see here now we have been discussing how this value is phi is equal to 2 pi. So, the value of phi now goes as 0, 2 pi, 4 phi if you look at any of the wave motion and consider the wave as a sine wave, we have the trough to trough or the crest to crest distance as lambda. So, if that is the wavelength, then we see that the change in the phase, that is from here to that particular point, is 180 degrees, that 180 in the down and 180 in the up. So, it will become 360 degrees. So, therefore, we have these kind of phases which will phases which are developing with respect to the individual planes. So, let me make it clear, we have a crystal. In that particular crystal, we have a plane passing through the origin 0 0 0, and this particular origin now will allow us the first diffraction to come out of this plane at a satisfaction of the path difference being lambda, and therefore, the phase difference is 2 pi. If you go in the opposite direction, the path difference is lambda and phase difference is minus 2 pi, and we can always develop many such parallel planes. It is also possible to have planes like that in a opposite direction, in another direction. You remember the bread analogy, we can cut the bread not always like this, we can always cut it along 1 1 1 plane or something like that. So, you can have a sandwich kind of bread. So, we can have these cutting of the slices in various possible directions. Now, the thing which we have to notice is that the amplitude of X-ray scattered by each atom in the unit cell is proportional to F. So, each atom now, the amplitude of X-ray scattered is proportional to F, and therefore, it depends upon the scattering angle. So, as we go to the higher and higher angles from 0 0 0, as we go to higher and higher angles of scattering, the value of F falls with respect to sin theta by lambda. The atomic position in the unit cell dictates the final amplitude. If the atom is at 0 0 0, the phase is 0. Okay. So, this is a point which one should remember. Now, what happens if the point is not with respect to the plane, and this is something which is of extreme importance, and we will discuss that in a minute. Now, suppose we have a 0 0 0 plane, just like that plane here, we have a 0 0 0 plane. The first diffraction will occur at a distance of d of HKL. Now, the second one will occur at 2 d HKL and so on. Suppose there is an atom XYZ at this position in the unit cell. So, there is an atom here and that is in the unit cell. So, what you do is you draw a plane which is parallel to the plane. So, in 2 dimensions we are drawing a line. So, this line which is there 1 d of HKL away, which is actually giving the scattering associated with it. What we do is we draw a line parallel to that. So, the XYZ is an atom which is now not at a distance of d of HKL, but at a distance of capital D of HKL. So, capital of D of HKL is the distance of the atom from the plane, and we have drawn a plane which is parallel to 0 0 0 and therefore, parallel passing through XYZ, but parallel to the first plane which is D of HKL. So, if that is the case, then what I have written will happen. Scattering is from the atom and not the plane, we know that very well now. So, phase difference of X-ray scattered by atom at XYZ and an atom at the origin. So, suppose there is an atom at 0 0 0 and another atom at XYZ. The atom at 0 0 0 there is no problem because the phase is 0. The atom at XYZ now will have a path difference of d of HKL. This is where the atom is located. So, the path difference of d of HKL, and this is where the plane is located. So, we are actually now calculating wherever be the atom, it does not matter, the contribution of that atom to the plane, because we are actually getting the experimental measurement in terms of the planes. So, the diffraction spot we get is from d of HKL, it is not coming from XYZ position, but the scattering is done by XYZ. And therefore, we have to consider d of HKL divided by this d of HKL slash lambda as the path difference, and therefore, the phase difference will be 2 pi d of HKL by small d of HKL. And so, we can calculate the corresponding phase difference associated with the atom being at some position XYZ with respect to the plane. So, now you can imagine the contribution of xyz to some other plane which may pass through the origin and it may go something like that. Then the first plane out will be there. So, then we have to calculate that d of HKL and the corresponding d of HKL. So, therefore, this atom now contributes to all the reflections. Go back to the very original idea we brought in, that is, when we have more than a wave coming out from a position, these waves can interfere. So, they can interfere constructively, they can interfere destructively, they can interfere with partial overlaps and so on. You remember that animation I showed of a sine curve. So, that therefore will tell us the contribution from xyz could be maximum to certain DHKL planes, could be minimum to certain DHKL planes and so on. And therefore, the intensity that is associated with the d of HKL plane, the contribution of this atom xyz to that plane is very crucial, and that comes out from this calculation that phase difference will be 2 pi d of HKL by d of HKL. So, how does it help? It helps in the following way if we take an example. So, what we are therefore going to do is to take an example to illustrate this one, and that is why I showed you the scattering factor curves of F versus sin theta by lambda corresponding to cesium plus and chlorine minus, the two ions, because these two ions form a compound which is CsCl, the cesium chloride. Cesium chloride is a salt, we know that. So, it exists as Cs plus and Cl minus. So, the scattering factor that the atomic scattering factor that contributes to this particular structure will come from the atom cesium plus, the ionic species cesium plus and the ionic species chlorine minus, and that is why we drew the curve earlier on of F versus sin theta by lambda. Let me take it back to you. So, this is the curve which we have, one for the cesium plus, the other for the chlorine minus. So, we can get the value of the atomic scattering factor at whatever be the scattering angle at which we find the diffraction spots. So, individually we can identify what is the contribution of cesium, what is the contribution of chlorine minus. So, if that is the case, then we should be able to construct a intensity profile associated with any HKL plane. See, in the case of cesium chloride, the structure is known. So, we are going to assume the structure. The cesium atom is sitting at the origin and it is a simple cubic structure. So, you will have it repeat again 1 unit away, 1 unit away and 1 unit away. So, this is our unit cell with cesium at 0 0 0 and chlorine sits at half half half. So, this is shown as at x equals half, y equals half and z is equal to half, half is indicated next to the atom. So, these are the positions of the two atoms, there is nothing else in this unit cell. So, we want to see what are the contributions these two atoms do or give to the individual reflections, because what we get from the diffraction experiment is the individual reflection that is associated with your HKL planes. So, how do we get that? So, we write the intensity of HKL. So, this is a very general expression for any intensity of HKL, we can write this expression. This is equal to sum over I equals 1 to n f of n cosine phi n, where phi n is the phase, square of that, plus sum over 1 to n f n sin phi of n square of that. That is because you see you have discussed earlier on the scattering factor and then eventually the structure factor. The structure factor was a complex number and the square of the structure factor gives us a value which is proportional to the intensity, and it is expressed as cosine plus I sine in the complex diagram. Since that is expressed as cosine plus I sine and that is our structure factor, when we want to square that quantity, what we will get will be this expression. So, therefore, the intensity of HKL is sum over 1 to n f n cosine phi n whole square plus sum over 1 to n f n sin phi n whole square. So, this is a general expression for intensities. Any compound intensity to any given HKL can be calculated based on how many atoms are there in the unit cell and what is their contribution to a given scattering angle. So, if you see in this particular case, there are only 2 atoms in the unit cell. This is summed over 1 to n all the atoms inside the unit cell. Sum over 1 to n all the atoms in the unit cell. So, if you have a 100 atom structure, obviously this calculation is going to be very difficult. It is obviously not the way to do it. So, at this moment we know what is the contribution of the intensity contribution of the individual atoms that is present in the structure. It depends upon where it is. The phase that is going to be associated will depend upon where it is sitting. So, in this particular case the chlorine atom is at 0 0 0 half and the cesium atom is at 0 0 0. So, let us calculate the contribution to intensity 1 0 0. So, intensity 1 0 0 will be at a distance of d HKL is d 1 0 0. So, the d HKL now is equal to A, the cell dimension. So, therefore, we are considering the plane which is passing through the value of d 1 0 0. So, if you this is the 3 dimensional structure, you have this line will now be the representation of d 1 0 0. Therefore, 1 0 0 plane is represented by horizontal line. So, this is your 1 0 0 direction, this is your 0 1 0 direction, and therefore, if you consider this point, it will be 1 along this and 1 along that. So, we therefore consider the contribution of d 1 0 0, the intensity of d 1 0 0. The intensity of d 1 0 0 in this particular example where we have only 2 atoms can be very easily written. That is because we can use this expression, expand it. So, we get f of Cs cosine 0 plus f of Cl cosine pi whole square. Now, why did I write cosine pi here? You all know by now what is the phase difference which comes if the atom is removed by the half the distance. So, we say that the path difference, the path length for the first plane which is out here, which is now at 1 0 0 in this direction, the path difference is lambda, and therefore, the phase difference is 2 pi, whereas the atom now is coming at a half position. So, we have to take the ratio of d of HKL to big D of HKL to small d of HKL. So, what is big D of HKL with respect to chlorine? You have to draw a line here parallel to 1 0 0, and that comes at half this position. So, if this is the value for the path difference of lambda, then this will be at the point which is equal to lambda divided by 2. That is because half of d 1 0 0 is half of A. Since it is half of A direction, we will have the path difference of lambda by 2, because with the full A, the path difference is lambda by definition of the Bragg's law. So, the atom now is sitting halfway between these. Since we now draw a parallel line, we calculate the path difference, or in fact the phase difference, as capital D of HKL by small d of HKL, and that will be equal to pi, because the path difference is lambda, the phase difference is pi. Path difference is lambda by 2, the phase difference is pi. Path difference is lambda, then the phase difference is 2 pi, which we have already seen. And therefore, the value of I of 1 0 0 goes like this: f of cosine 0 plus f of Cl cosine pi square, f Cs sine 0 plus f Cl sine pi square. So, this can be calculated. We know how the cosine behavior takes place and how the sine function varies with respect to the angular variation, and so this turns out to be f Cs minus f of Cl square. So, the intensity of 1 0 0 is the difference between the atomic scattering factor of cesium ion minus the atomic scattering of chlorine ion. We have to find out where this I 1 0 0 will come. See, I 1 0 0 is not going to come at the scattering angle theta equals 0, it will come at a certain theta value. One can calculate where that theta value can come and that particular value of f should be taken from this curve. So, it is not going to be 54 and 18 contribution, it is going to be something different, and that something different will come from the value of sin theta by lambda. We will see how it comes up. So, what is happening here is that the d 1 0 0 represents a plane which is passing through this cesium atom. Similarly, d 2 0 0, which is A by 2, passes through the cesium atom, the chlorine atom. Now, the cesium atom is now removed, there is no cesium atom associated with 200, but what is the contribution to the intensity? This is very interesting. There is no the cesium atom is at 000. As you know that any atom at 000 will always contribute with a phase change of 0 degrees. That is because the path length is 0 and the phase difference is 0. So, we have therefore I200, we have the scattering factor of Cs cosine 0. For chlorine now it becomes cosine 2 pi, because now D200 is the one which is the first plane out of the after 000, and therefore, it will now have a path difference of lambda. So, the phase difference is 2 pi. So, we get FCS cosine 0 plus FCL cosine 0 square. So, when you put these values in, and then you will see that this turns out to be FCS plus FCL square. The only interesting point here we have to notice is that we have to see that corresponding sin theta by lambda value which will come for D100 and the corresponding sin theta by lambda which will come from 2100, and read out the corresponding FCS FCL values. That means, if you go back here, the 100 may come corresponding to these 2 points, 200 may come corresponding to those 2 points. So, the value of F will not be now 54 and 18, it will be much lower. So, as you go to the higher angles from 100 to 200, the value of FCS and FCL will reduce. However, you see that the contribution to the intensity 200 comes out as F of CS plus F of CL square. So, it may be that even though FCS, FCL individual values are lower, the contribution to the I200 will be much higher because they are adding up, whereas in this particular case the contribution is subtracting. So, the individual values of the scattering powers of cesium and chlorine may be higher for 100 case because of this position in the sin theta by lambda, where we have to read out the corresponding F value. On the other hand, the 200 will be farther away in sin theta by lambda, but since there is an addition here, this value may be much higher than that value. We will see what are those values which will come as in a few minutes. So, how does this happen? This happens because D200 is half of D100, and that is therefore 2 pi times half of A. This is capital D HKL by small d HKL. The capital D HKL is half A. The small d HKL is also half A because we are now considering the reflection 200, which is halfway between 100 and the origin, and therefore, we have a 2 pi value corresponding to the phase difference, and that is what has appeared here. So, if you now study this carefully once more, this particular slide, you will see that it is very easy to identify how these contributions are coming. So, when we consider the 210 plane, chlorine atom will lie midway between the lattice planes to D210. So, it will get 3 by 2 D210. Let me indicate where 210 is, it is here. So, this is the D210. We are now calculating the contribution from cesium as well as from chlorine. We do not have to worry about contribution from cesium because it is sitting at the origin. So, it contributes equally to all the reflections because the atom is at the origin. Okay. So, since the atom is at the origin, it contributes to all the reflections equally. There is no difference in path, there is no difference in phase. So, whether the plane is here parallel like that D100, D200, D300, or a plane which is going now like this. This is now 1 unit along y and half a unit along x. So, therefore, this is the D210 plane corresponding to D210. This is the plane 210, and you see that the plane 210 is the chlorine atom now sits halfway between these two, and so if you calculate that value, it turns out that it is at 3 by 2 D210. So, the X-rays scattered by chlorine atom at half into this reflection will be 2 pi times 3 by 2, that happens to be 3 pi. So, 210 therefore, you can calculate, you have Fc cosine 0, that does not change, but FCL cosine becomes 3 pi now, square of that, and the sine part also becomes square. So, the value can be calculated as FCS minus FCL square. So, the reflections 100, 200 and 210, they do not appear as we again discussed earlier on with the figures. The values of FCS plus and FCL minus are to be taken corresponding to the 2 theta values of these reflections in the f versus sin theta by lambda curve, these values. So, we have to pick up those values of the f. So, if we do that, then we will be able to calculate what should be the contribution of cesium chloride to these individual reflections. Now, imagine a structure which has 100 atoms. You have a unit cell, let us say 8 by 10 by 12, an orthorhombic unit cell. So, you can actually generate how many possible planes can be created, because we now know how to generate the planes. The planes need not be along a or a B or a C direction. This is our bread analogy. We can cut this loaf of bread in any orientation we want, and each loaf, each slice will now represent a plane. So, the bread can be cut like this, bread can be cut like that, bread can be cut along a diagonal and so on. So, if you cut the bread along the diagonal, the first plane out at the middle at the A equals 1, B equals 1, C equals 1 will be the 1 1 1 plane. So, all planes which are parallel to 1 1 1 can come if we keep slicing the loaf in that particular direction. So, therefore, we now know how to calculate the contributions for the individual reflections. So, suppose there are 100 atoms, each and every atom wherever it is sitting will contribute to this. So, it is not going to be a very easy task. Here we have taken 2 atoms, we have taken a cesium at origin and chlorine at half. Very easy to see how these are all coming, but when we have 100 atoms in a x1, xn, yn, zn positions, randomly distributed but covered, remember it is in the crystal, so it is always covered by symmetry rules. So, we have our symmetry rules validated anyway. So, keeping the symmetry rules in mind, we will have these atoms, but still it is a large number of atoms, and this is not the way in which we should be calculating. However, if you want to see how the cesium chloride behaves, this is a chart which I am giving you. This chart tells you the following. This is a simple cubic, as we said. So, A is equal to 4.123. It so happens the unit cell dimensions are all 1, 2, 3, 4 is by chance. So, A is 4.123 angstroms, cesium is 0 and chlorine at half. So, we can calculate the HKL 100, what should be the intensity for that. So, we get the D of HKL, which is equal to A in this particular case, because 100 is the reflection we are considering. So, if we calculate the sin theta by lambda using the formula 1 by 2 D HKL, we will get 1 by 2 A is equal to 0.12. So, this is the value of sin theta by lambda. So, corresponding to 0.12, you have to read out the cesium and the chlorine scattering factors. So, let us go back and see how to do that. So, here you take the value of 0.12 somewhere here. So, you will have to now read the chlorine contribution and read the cesium chloride contribution at 0.12. Now, the 0.12 values are in fact given in this table. The table gives you the values to be coming in such a way that the difference in these two, the value of f of Cs is 50, not 54. For chlorine it is not 18, it is 15. So, there is a reduction in the contribution of the individual atom. So, even though we have a cesium plus and a chlorine minus in this structure, the contribution from cesium and chlorine is coming as though the atoms have only 50 electrons and 15 electrons in these two cases. The ions have only 50 electrons and 15 electrons. So, this is something which you must remember when you do the calculation, and so we therefore have already seen what is 100 in the previous view graph, that is FCS minus FCL whole square. So, the difference 50 minus 15 is 35 square. So, we get an intensity of 1225. We get an intensity of 1225. So, similarly we can do for 200, 300, 210, 420, depending upon the value of D. We substitute this value of D up here, we get the sin theta by lambda value. You see that the sin theta by lambda value keeps on increasing, and correspondingly the value of Cs and Cl keeps on decreasing, and depending upon where the FCS, FCl values are, for example, 300 is a reflection which comes after 210, and therefore you see the contribution is 41 and 10 here and 36 and 8 there. But what is more important is the way in which the phase addition takes place, and therefore here you have FCS plus FCl giving you 2809 as the intensity. This intensity is in absolute value because we do not have anything else other than these electrons. So these are therefore showing the absolute value, and the absolute values are now 1225, 2809. You see that even though this is FCS minus FCl square, even though the values are 28 and 7, the contribution of 420 is very large. So you get a value of 1225. So what does it all mean? What it means is now you take cesium chloride crystal, put it in the path of the X-ray beam and do a diffraction pattern. What I will show you, instead of showing the spots which will appear for these individual reflections, I will show you a powder diffraction diagram which is simulated. See, we know where cesium is sitting and where chlorine is sitting. So I took it out from the web, and this is the XRD pattern of cesium chloride. So you see now that this is the intensity and this is the 2 theta. You see here the intensity values are given some numbers here. So why is that given like that? It depends upon the instrument you are using. So this is therefore what we can call as the relative intensity. It is not the absolute intensity, but you see that the first reflection and the second reflection is 100 and 200, and you see the values were 1225 and 2800. Okay. So you see the relative variations of the intensities in the powder pattern. So the powder pattern or the single crystal pattern, suppose this was single crystal. In fact, the simulated pattern is very useful because you draw a single line. In case of the single crystal, you get a spot here corresponding to this intensity, a spot there corresponding to that intensity, and so on. So this is therefore the plot of the cesium chloride X-ray diffraction pattern. So now you see a 1-to-1 correspondence for the first time. You see the diffraction occurring. The diffraction therefore, as I have made you believe, and now you know very well, very thoroughly, that it is now associated only with the planes. Atoms are sitting at 0, 0, 0 and half, half, half. But the X-ray diffraction pattern is produced from the planes, and you have calculated yourself the contribution to each of these planes in case of cesium chloride, and you see that behavior is shown in the X-ray diffraction pattern. And what you have calculated, of course, is a little more sacred than this, in the sense that you have calculated the absolute intensities. So what you have to therefore do is to convert the relative intensity you have got in the X-ray experiment to the absolute intensity. There are so many other factors which are involved to do that operation. We will see how we do it at a later date when we actually determine the structures. But at this particular point, we see that the intensities can be calculated. If you have a very simple structure like cesium chloride, where we know already the structure, cesium is at 0, 0, 0 and chlorine is at half, 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 then it is very straightforward as we have done now. And we also now know how the pattern arises because of the positions of these atoms. But what is more important is to take a case where we do not know where the atoms are. Suppose we had a cesium chloride structure where we had not solved the structure, then there is no way I would have done this calculation. So there is no way I would have got these relative intensities. However, if I had recorded a powder pattern, I would have got this powder pattern. This is for reality. So you have the cesium chloride sample and you powdered the cesium chloride crystal and recorded the powder pattern. Of course, this is a simulated pattern, so it does not give you any widths. In a typical powder pattern, there is a certain width associated with it. This we will all discuss when we go to powder diffraction methodology, which is very crucial, particularly for the pharma industry people, to remember that there will be a certain width with each of these peak positions, and that is very crucial. So effectively, this is the intensity we will get when we put the cesium and chlorine in known positions and calculate the corresponding contributions to individual reflections. So X-ray diffraction pattern therefore is coming from the planes, and the atoms need not sit in any plane, they can sit wherever they want, but their contribution to the plane can be calculated, just as we have done in the case of cesium chloride. I think this kind of brings us to a stage where we can stop at this juncture. because what we are going to do next will be a situation where we can get to the general expression to calculate the intensities. So, we cannot all the time calculate the intensities this way, which we did. For example, in this case we have the intensity expression which is a general expression, but then we cannot get the every time where the atoms are sitting and with respect to them calculate this. This is a very simple calculation where we had only 2 atoms in the unit cell, but if there are more atoms in the unit cell and they are distributed all over the unit cell, how do we get to that position? How do we calculate the intensity? So, we have to have a general formula. So, the next job would be to generate a general formula by means of which we can calculate the intensity given the atom positions. We still given the atom positions. If the atom positions have to be determined, that is the next step, which is our structure determination. We do not know where the atoms are, but we do have the experimental data now which gives us the I versus 2 theta plot. Whether it is a powder diffraction or if it is a single crystal, we get the individual reciprocal lattice points which can be indexed and the intensities can be measured. So, we have reached a stage of let us say it is a mid level stage of this particular course where we have more or less covered all the aspects of symmetry, all the aspects that are associated with space groups and so on, how we generate the equivalent points. Now, we have also found a situation how the atoms sitting in different positions contribute to the intensities of individual reflections.